The Kelvin-Helmholtz instability, have you done any experiment on it? No? Okay, then even better. So the one thing you will see is that visualizing that instability is 16 to 20 times harder in air compared to water, and the reason will become clear to you in some time. So let's do that. So yesterday we discussed Rayleigh-Taylor, and some of you, we were having discussion about this pollution problem in Delhi. And so Rayleigh-Taylor is a very direct answer to the question of why you have so much pollution or why you feel so much pollution in Delhi in winters rather than summers. So the reasons that are plaguing this pollution exist throughout the year. It's not like things are happening in winter which are very different compared to summer, but still you feel it a lot in winters compared to summers, and the reason is actually somewhere rooted in the Rayleigh-Taylor instability problem. And the thing is that when you have a temperature gradient which is, let us say, decreasing, okay, you have temperature that is decreasing with gravity, that is decreasing as you go up, then we saw that as a result of this you have density that will be, so density, if this is high, you will have density varying like this, okay, density will be higher below and low, density will be lower below and higher above. So it's an inherently unstable case. Okay, this is called unstable stratification. Basically, stratification, the word you can understand, it's layers or strata that are formed, and you have strata which are unstably lying on top of each other. You have heavier fluid lying on top of lighter fluid, that is unstable. And this is what happens in summers. The air, atmospheric air closer to the ground is hotter compared to the compared to what happens in winters. So in summers, the atmospheric conditions are in an unstable stratified condition. So whatever dust and dust, cement and smoke and everything that you are ejecting out, that quickly goes around and gets convected above. Okay, that keeps getting mixed, it doesn't accumulate. Okay, it doesn't accumulate because there are, once you have these unstable stratification, so if you looked at the textbook, then you can show that the growth rate is always there, growth rate is always, the I omega part is always real. And so what you will see is, once you have an unstable stratification, you form these convection currents. Okay, these convection currents keep the flow mixed in summers, keep the atmospheric flow mixed in summers, and that, of course, atmospheric flow is not like, atmosphere is not stable, there is an atmospheric boundary layer, because you have an atmosphere, you have an earth that is rotating. Okay, so if you really think about it, atmosphere is not stationary, atmosphere is like a layer of fluid and you have a solid that is rotating, so there will be a boundary layer type of a phenomena that will be formed. Okay, but even within that boundary layer you can have this unstable stratification, which is the case what happens in summers, and in winters you have the opposite of this. You have the temperature that is varying, that is less closer to the ground, and it, so it's not like it keeps on increasing, of course after reaching some point in the atmosphere it will decrease again. Okay, but closer to the ground you have this positive temperature gradient. As a result of that, you have the density which is lower, which is higher here, and density decreases as you move up in y. Okay, this is your t, this is your rho, and this is y. So this is, according to Rayleigh-Taylor, this is a stable stratification. There's no instability that is going to happen here. If you have a lighter fluid resting on top of heavier fluid, there's no instability. And if you think about buoyancy, if this guy is a fluid parcel that has slightly higher density, that is slightly lower density, it will move up. Okay, if it moves up due to buoyancy, the density difference between the surroundings and its own density will be decreased now. So the feedback that we discussed towards end of last lecture is negative feedback loop now. As it moves up, the buoyancy force decreases. So if it keeps moving up, the buoyancy force keeps decreasing, and at some point of time it will just keep resting there. But on the other hand, here, if you have a fluid parcel which has a density which is lower than its surroundings, okay, let's say this is density lower than surroundings at this location, if it moves up, it sees even greater density difference. It further moves up, the buoyancy force further increases and it keeps increasing further, and that's the positive feedback loop. So in winters, what you see is a stable stratification which makes the pollution, which makes you feel the pollution a bit more. You see it more, it's not mixed, it's accumulated. It's there in summers as well. Okay, so that's a very nice way to think about real world applications of where you could observe Rayleigh-Taylor instability. And now the instability that we are going to look at today, which is Kelvin-Helmholtz, that is also very much realistically observed. If you just go at some places where you can see the clear sky at least, then you will see that you can see clouds that are formed in this shape. Okay, so clouds are formed in this shape, for example. They will have some bulbs out of them coming out, and those bulbs will have some deformation. Okay, you will see this kind of a phenomena that happens when clouds form. And the reason why this happens is because you have two fluid streams or two flow streams. So something like what we discussed in boundary layer theory, a mixing layer. You have, let us say, a mixing layer, and what happens is, as this keeps on flowing, there are unstable perturbations which grow, okay, which grow in time. Okay, and we'll try to see that visualization today in this model wind tunnel. So let us say you have this density stratification. You have density, let's say rho 1, rho 2, rho 3, rho 4, rho 5, rho 6. So I will explain one case, I'll expect you to understand the other case. Okay, let's say the density as you go down is decreasing, increasing. So rho 1 is higher than rho 2, higher than rho 3, higher than rho 4, higher than rho 5, higher than rho 6. Okay, something like this case. Okay, let's say you have a fluid particle which belongs to this layer. Okay, or rather a fluid particle which belongs somewhere in between rho 1 and rho 2 layer. Okay, let's say the density of the fluid particle gets perturbed a little bit and it becomes lower than whatever you have here. Okay, the dense, so until unless you add some perturbations, you can't see instability. Instability relies on some perturbations which will grow to infinity. Zero values can't grow to infinity. Zero values can't grow exponentially in time. Even if you multiply 0 with exponential positive times t, it will still be 0. So you have to have some perturbation. So you add some perturbation, and let us say rho p is lesser than whatever you have, let's say rho 1 plus rho 2 by 2. There is a difference between their density. The particle is lighter due to buoyancy, it will move up. When it moves up, let us say it comes here, the density difference will be larger now, because rho 2 will be greater than rho 1 plus rho 2 by 2. So, if the density difference is larger, then the particle sees even higher buoyancy force. Now it's in the rho 2 region, and so the particle density. Particle maintains its own density. Okay, this was the continuity equation. For incompressible flows, this guy was not there. Okay, for incompressible, even with varying density, we saw that you have this. If you go back to a non-dimensionalization discussion, we said that this happens at, so this happens at leading order, and then this happens at higher order. These are two different orders of terms. So particle's density remains constant. As the particle moves, its density gets convected up with itself. Density of the particle. Yeah, yeah, yeah. So that would mean that it will go up slightly. And now as it goes up, it sees. Now the density of the surrounding is slightly lesser now. It's no, density of the surrounding is larger. Rho 2 is greater than rho 1. No. Okay. Hold on. So this is your density. Okay, this is the stable stratification case. Yes, you're right. So rho 2 is less than rho 1. So if rho 2 is less than rho 1, so when the particle moves up, the buoyancy force will be slightly decreased actually in this case.
It should sort of oscillate.
No. Yeah. So uh, there is a concept of you can show that in some cases you will have some oscillations also here. Actually, the oscillations are connected to viscosity, which is very funny here, but it won't oscillate. So it will, because there is no technically for oscillation you need a restoring force. There is no restoring force. It's just the force that was moving it up decreased. It's not that there is an opposite force.
But there is no force driving it upwards also.
Yeah. So what will happen is it will move slightly up and then stay at a place where it is neutrally buoyant, because if you decrease its density it will find some place up where the density of fluid layer is equal to its density and it will just stay there. It's a neutrally buoyant particle.
By this logic, in the Winter's case, right, it should go up.
No, so Winters is density. Density. So here density is increasing downwards, not decreasing downwards.
This
It's
is like summers.
this is like Winters. Then density is increasing because temperature is reducing. You have colder air, so you have denser air. Density is, hold on, density is increasing downwards. So rho 1 is greater than rho 2, greater than rho 3. So this is density. Yeah. Rho is decreasing upwards. Yeah.
That's why you're saying that in winter sort of
Stays there. It'll go up. It'll keep going up, and there'll be convection currents that form. Okay, so let us look at this problem of Kelvin-Helmholtz instability, and we'll attack it from a fluid interface point of view. And so in the textbook you can see the example where you have two fluid streams of different velocities. So let's say you have rho 1 u1 and rho 2 u2. Okay, let us try to do this only in 2D. You can extend this analysis in 3D very easily. Okay, because as you will see, x and z both will be homogeneous directions, so you can just extend another, add another wave number for your normal mode assumption and continue with your analysis. So let us look at the instability, and what we are going to look at is the case is inviscid. We are assuming inviscid flow. Okay, we are assuming inviscid flow. So when you have inviscid flow, we'll write that okay, del square phi1 is 0 and del square phi2 is 0, where phi1 is the velocity potential in the top fluid and phi2 is the velocity potential in the bottom fluid. Okay, so what is the base state? Base state is simply, so base state is your phi1 is simply u1x. Okay, because grad of phi1 has to give you velocity. Okay, so phi1 is simply u1x, phi2 is simply u2x. Okay, so phi1 is this, phi2 is this, and now what do we do about the other terms? So is this all? In the base state we also have to get pressure. Actually here it's p1 and here it's p2.
direction of the velocity is
Okay, at the top it's p1, at the bottom it's p2. Okay, what is the dynamic interface condition? What does the dynamic interface condition give you? The dynamic interface condition gives us that. So I would not put the not subscript right now. We will do that when we have derived all the base state variables, base state flow variables. So P1 is equal to P2 from the dynamic interface condition, because the dynamic interface condition says that the dynamic interface condition says what? The stress or the traction vector is equal. Okay, traction vector doesn't have anything else except for viscosity here. Traction vector, I mean, traction vector doesn't have anything else except for pressure. There's no viscosity in this system. Okay, so you don't have any viscous stresses, you just have pressure stress, and so from that you have P1 n cap, P2 n cap that are equal. Okay, so that means P1 and P2 are equal. If we were considering two fluid streams such that there was a surface tension coefficient here, right now I am assuming that the surface tension coefficient is 0. If we were doing a case where surface tension coefficient was there, then you would take P1 minus P2 equals sigma del dot n. Okay, yeah, u1 is constant, u2 is constant, both in x and y. Okay, it's an inviscid flow, so we can have that. If this was viscous flow, then we will have a developing shear layer. Okay, we are looking at an inviscid flow to avoid those complications exactly. So this is our base flow solution. Pressures are same and this is it. Okay, there is another equation that you can apply inside the flow here, and that is the unsteady Bernoulli's equation, the governing equation for the governing equation that relates phi1 and p1, that is the del phi1 by del t. If you recall, you can derive it from your velocity potential. So you have, for the inviscid flow, you have this. Uh, okay, for the inviscid flow you have this. If you substitute u is grad phi, okay, then you can write this equation as del by del t of phi plus grad of p by rho plus grad phi dot square by 2. Now here I did some cheating, and the cheating is that I was able to write grad p by rho as grad of p by rho. The only region where I can do this is either all in y greater than 0 or y less than 0 separately. I cannot do it across the interface, because across the interface density is not constant. So that means the equation that you have derived, this equation, and then when you write this, that del phi by del t plus p by rho plus this square by 2 equals a constant, let us say c. This whole equation will have different 1 and 2 subscripts in different fluid streams. Okay, you will have this, and then you can have this. So P1 comma 2 rho 1 comma 2. So basically it means for 1 and 2 you have to write the equation separately. The constants C1 and C2 will be different, they can't be same. Okay. So what do we get from here? These constants we will get for the base flow, we will constants these constants will get that C1. So you see C1 will be equal to what? P1 by rho 1 plus U1 square by 2, and then C2 will be P2 over rho 2 plus U2 square by 2. Okay. Now since all of this is base state, okay, I'll keep the velocity with the capital U's here, or actually let's just keep the base state. Yeah, let's write the base state with a subscript 0. Okay, so we have phi1 0, phi2 0. Okay, I will not put zeros in front of u1 and u2 because they are given. I'll put them in front of the variables that we are solving for.
So this C1 and C2 is for a steady flow, right?
Hmm?
This C1 and C2 that you have.
So C1 and C2, these guys are constants in space, and they will have some function of time. Okay, the governing equation is as it is.
Why del phi or del t?
For now we are saying this is base state.
So that is steady.
Base state, so this term is gone. Okay, so it's like saying that when we have unsteady flow, it will be equal to C1, but we will not keep make this go to 0, because this is the governing equation. Okay, from the governing equation and by substituting base flow in it, we found this constant. Okay, we found this constant from that. So now we will put perturbations and we will say phi 1 is this phi 1 naught plus epsilon phi 1 prime, phi 2 is this phi 2 naught plus epsilon phi 2 prime, and P1 is this P1 naught plus epsilon P1 prime, P2 is P2 naught plus epsilon P2 prime. And what we will see is say is that this interface, which was y equal to 0, the interface is that y is equal to epsilon c prime x comma t. Of course, your phi 1 prime is x comma y comma t. All of these guys are x comma y comma t. Okay. So the governing equation for your phi 1 is simply this. Phi 1 0 satisfies this equation. So this means del square of phi 1 prime is 0. Similarly for phi 2, okay. What is the kinematic interface condition? So here we did not need any kinematic interface condition because the y direction velocity is 0, and since we are not dealing with viscous flows, we do not have to impose any no slip at the interface. Okay. This means no need for no slip at the interface. So the kinematic interface condition is basically that the normal velocities are equal on both the sides of the interface. So what is the normal velocity on both the sides? How do we calculate this normal velocity? So n dot grad phi 1 is equal to this is the kinematic interface condition. Okay. And this normal velocity is equal to what? How do we calculate what is this normal velocity equal to? So y minus epsilon c prime x comma t is some capital F x comma y comma t, and that is constant. That is how the interface is defined. So we say that df by dt is 0, right. So that means epsilon del c prime by del t plus, what do we have here? So u dot grad of f equals 0. What is u dot grad of f? What is grad of f? So u is, let us say, this guy. Okay. So this is I cap plus u prime vector dot grad of f. What is grad of f? J cap minus epsilon del c prime by del x I cap. Okay. So linearized equation gives del c prime by del t with an epsilon plus, what is the linear term that you can have here? What is the only linear term that you can have? Del c prime by del s, that is c. Okay. Now, no one else will have a linear term, will it? There will be a linear term from here also, right? Yeah, base flow is I cap, but this guy will give you a linear term. So plus epsilon, let's say v prime. Okay, and v prime we know is going to be del phi prime by del y. Okay. So from here we get that del c prime by del t equals capital U del c prime by del x minus and a del phi prime over del y. Okay. And we will have to apply this equation for both 1 and 2 separately. So here will be 1 comma 2 u 1 comma 2. Okay. And let us now evaluate this linearized form of this equation. So n cap n hat we know is grad f by mod grad f. Okay. n hat is grad f by mod grad f. So that is nothing but j cap minus epsilon del c prime over del x I cap by its magnitude, which we can approximate as 1 because that will give us a epsilon square term. Okay. So what do we get here? Del phi 1. So phi 1, let's substitute. So we have u1 x, or rather u1 I cap plus epsilon u1 prime vector dot with this guy j cap minus epsilon del c prime over del x I cap with the magnitude equals j cap minus epsilon del c prime over del x I cap divided with the magnitude dot with u2 I cap plus epsilon u2 prime. What is the linear term that we get here? What is the linear term that we can get from here? So what do we get? So minus epsilon del c prime over del x u1 plus u1 prime, okay, plus u1 or sorry v1 prime equals minus epsilon del c prime over del x times u2 plus v2 prime. Okay. So we just showed that you will get the same term here because u1 del c prime by del x minus of del phi 1 prime by del y is equal to the other guy. So del c prime by del t is same from both the sides. Okay. So by writing this, you don't really get any more information, you just get a confirmation that this holds for both sides. Okay. You can write del c prime by del t in terms of variables at the top flow stream and the bottom flow stream, and whatever you have on the right hand side, they are equal because you have equated the normal velocity. Okay. So this makes your analysis, this confirms that your analysis is going in a consistent way. And so once you have the kinematic interface condition, let us look at the dynamic interface condition. Okay. So when we look at dynamic interface condition, we have to be, so we will have to use this. Okay. Let us see how we will use this. So we know in the top flow stream, we have del phi 1 by del t plus p1 by rho 1 plus grad phi 1 square by 2 equals c1, and then in the bottom one, so for y greater than 0, and we know this for y less than 0, and we know that the dynamic interface condition says that p1 equals p2 for at actually y greater than epsilon c prime, let's put it. Okay. Remember that again we make the convenience here that this is applied at y equal to epsilon c prime, and then you again apply the Taylor expansion to just say, okay, just like we did in Rayleigh-Plateau and all our linear analysis, you just apply in the linear up to linear approximation, you can apply it at y equal to 0. Okay, up to linear approximation, same thing we will do here. Let's just simplify. So I'm writing this just for being exact, but after linearization you can bring them, you can apply them at y equal to 0. So looking at this p1 equals p2, what you can do is you can multiply this equation by rho 1, you can multiply this equation by rho 2, and substitute p1 and p2 here. So what you can do is that rho 1 times this equals rho 2 times this, at y equal to epsilon c prime.
But to clarify what's been done in the bottom here, with below after we have the linearized. Confirm there.
So from this equation, okay, from this equation you will have this, okay. Now the velocity, so this equation is at interface at y equal to epsilon c prime, okay. You can apply this equation slightly, just ever so slightly above the interface and below the interface. So you could have u1 plus epsilon u1 prime or u2 plus epsilon u2 prime as well. The question is, from both the sides you will get that this term is equal and it is equal to this del c prime by del t, okay. Where do you get that they are equal? So this condition, the kinematic interface condition, that normal velocities are equal, that's what asserts that physically the right hand sides are equal. That's all, because we have seen previously also that this del c prime by del t, you can write it as a normal velocity divided by some constant, okay. So it's not very different from this normal velocity. So what right hand side linearized form is actually equal to the normal velocity that you have in the flow, and they are equal. That's what I've shown here. Basically you get this. Still there is a doubt, I guess. No, that's okay.
What df by dt means? Why are we putting both capital D and
Because f is constant for a material. So what we are saying is that you have a material point, okay. Interface is defined by a material point, okay. Interface is defined by a material point. What is that material point? If you have a material point which has, let us say, half of this fluid 2, half of this fluid 1, and this material point is moving in space. If a collection of these material points, you see them moving in space, then from a zoomed out view you will see that interface is moving in space. So interface is basically, as the interface moves, it's the material points that are moving. So for the definition of interface, at interface this capital F is constant. So df by dt is 0, material derivative, because it's constant at the interface and interface is a material point. So df by dt equals 0 means this, and when I apply this I get this at the linearized approximation. And all I have done is that, so here you will get that del c prime by del t equals this with one subscript, and it's equal to this with two subscript as well. I am just showing that that one subscript, two subscript RHSs are indeed equal to each other from the normal velocity equality. I am just showing that, okay. So now that we have this, we can substitute linearization here. What do we get when we substitute the perturbation expansion? We'll get, so phi 1 doesn't have any unsteady term, so epsilon phi 1 prime, phi 1 naught doesn't have any unsteady term, and we'll have a linearization from here. So u1 I cap plus, let's say, grad phi 1 prime or epsilon u1 prime, yeah, grad let's write it like this, dot with itself, okay. And then we have the values of c1. C1 is this, c1 is this, okay. Here we have p1 naught and p2 naught. So c1 is that, so we will have minus p1 naught by rho 1 minus u1 square by 2, okay. I'm just evaluating the left hand side, the right hand side will be same with subscripts 2, okay. So what is the order epsilon thing that you get from here? Hmm? Just a second, just a second. Let me make sure that I didn't do any mistake here. Yeah, I'm okay. I'm ignoring gravity in the analysis. Yes. Okay, that's okay. We can proceed by ignoring gravity also. So one, yeah, okay. Yes, there is a half here. Yes, okay. So what do we get here? Epsilon del phi 1 prime by del t plus half of u1 square by 2 plus u1 del phi 1 prime by del x. okay, because you will have a u1 I cap dot grad phi 1 prime 2 times. You are taking dot product with itself. So, you will have 2 terms u1 dot epsilon grad phi 1 prime, epsilon grad phi 1 prime dot u1. 2 of them with a half, they give you this. Okay, I cap dot grad phi 1 prime is del phi 1 prime by del x only. And then the other term, so this is with epsilon and the other term is order epsilon square. So, we drop it. Okay. And then you have minus p1 naught by rho 1 minus u1 square by 2. So, this is a good sign because your base state terms are cancelling out. Base state terms are cancelling out. And then what you get? Rho 1. So, on the left hand side you are left with epsilon rho 1 del phi 1 prime by del t plus u1 del phi 1 prime by del x and then a minus of p1 0. Actually rho 1 will be in multiplication of this. This will be equal to epsilon rho 2 del phi 2 prime by del t plus u2 del phi 2 prime by del x minus p2 0. Yeah.
How did you cancel the u1 square terms? That's u1 square by 4 and u1 square by 4.
Oh, so there won't be additional half. So there is u1 dot u1 u1 square by 2. And then p1 0 is equal to p2 0 we know from the base state. Okay. So, p1 0 and p2 0 cancel out. So, the linearized dynamic interface condition actually gives you linearized eraser. The linearized dynamic interface condition actually gives us that rho 1 times del phi 1 prime by del t plus u1 equals rho 2 now again this is at y equal to epsilon c prime and then we will linearize this further like we do and apply at y equal to 0, okay, by doing Taylor expansion. So, this is our linearized dynamic interface condition and then we have the linearized kinematic interface condition that del c prime by del t is equal to u1 del c prime by del x minus del phi 1 prime by del y which is equal to u2 del c2 prime by del x minus del phi 2 prime by del y. And now we have our linearized system of equations and this is for phi 1 prime and phi 2 prime and now we can substitute the normal mode assumption. What are the normal modes assumption? What is the normal modes assumption? What are the homogeneous directions here? X is the only homogeneous direction. So, phi 1 comma 2 prime you can expand as a function of y simply, okay, and of course there is minus infinity, okay, and so this is of course a function of omega also. So, this is a function of y, k and omega, okay. Yeah.
Xi2 primes.
Oh, sorry, yeah, you're right. There's no reason for doing that. It's the same. And now we know that del square phi 1 prime is 0 and del square phi 2 prime is 0. So, that means we will have d2 phi 1 hat by dy square and then what will be the second derivative in x? What will the second derivative in x give? Minus k square phi 1 hat equals 0. and then similarly d2 of phi 1 hat by dy square minus k square phi 2 hat equals 0. So, the general solution of phi 1 hat is simply a e to the power ky plus b e to the power minus ky, and then phi 2 hat is, let us say, c e to the power ky plus d e to the power minus ky. And then we will say that phi 1 hat has to go to 0 for y tends to infinity, and phi 2 hat has to go to 0 for y tends to minus infinity. Okay. So, that means a is 0 here, and this means that d is 0 here. Okay. So, the phi 2 hat is an exponentially increasing function in y, but for y less than 0, and phi 1 hat is an exponentially decreasing function of y for y greater than 0. Okay.
Why would Phi1 move to 0 at y infinity?
Perturbations are going to 0 for y tends to infinity. There are no perturbations. So, the way perturbations are added, and you will hopefully see it here, the way perturbations are added is through a perturbation in interface. Let us say you have a straight interface and everything was hunky dory before then, and then slight perturbation in interface adds these perturbations in velocity and pressure, and they result in everything. And the moment we add some perturbations slightly in incompressible flows, okay, especially kinematic perturbations in incompressible flows, it is safe to assume that perturbations far above are always 0 for all times. Okay. Do you guys have a class after this? So, okay, maybe let us try to do a demonstration now. We will try to solve this afterwards. Is unobstructed, so it moves as it is. Okay. Now, what is the, let us say, okay, we will ask this question later on, because if you look at online, let us say you look at YouTube videos of Kelvin-Helmholtz instability, if that is what works for you, then you will see that mostly it is shown in water, not in air. You guys can take a seat. It is shown in, is easier to see it from the naked eye. Okay, hopefully it works. Right. So, if you record it, have you recorded it?
Yeah.
Slow mo? Okay, now I am going to shut it off because there is a lot of smoke going on. Now we can switch on the lights. Rollers. Okay, and this is the instability that we are trying to analyze, and you will see it in the next class that a fluid stream which has a velocity difference is always unstable. There are some density changes that you can add which can make it stabilize, which can stabilize it, but inherently without any density changes it will be always unstable. Or even with stable stratification, basically density changes will not play too much of a role. The density difference between the smoke and air also is not too much here. Okay, the smoke is not adding too much density to the air. And one interesting thing that you see about this instability, you see this growth. Okay, which one is it? Is it temporal or convective instability? It is convective. Okay, so all the temporal analysis that we are doing in our class, it's actually limited in. So what you can do is you can maybe, so if you see these perturbations, you can highlight them within this region, let us say. You can extend a periodic domain and you can understand how they are growing in time. That's where the temporal analysis, power of temporal analysis actually comes. Maybe you can play it again. You can forget about this development and you can make the analysis assuming x direction to be homogeneous. Okay, you can understand convective instabilities from temporal from temporal perspective also, or you can do a pure convective instability analysis, and there you will not have a growth rate in time. Here if you see that if you basically look at only one spatial location, nothing is growing in time. But if you follow a roller, you will see that it grows in time. Okay. So, you can do the convective analysis in a stationary reference frame, or you can do a temporal analysis in a convecting reference frame as well. Okay. Both are valid choices. The wave speed that you will get will be different in both. Okay, because in the convective analysis you will have the wave speed added to the flow speed. But if you are moving with the reference frame of one of the rollers, let us say like this, then you will actually get the let us say you are not moving with the roller, but you are moving with the flow. Then you will get some displacement of the roller as you see it in time, and that will be the actual wave speed. The wave speed that you got in temporal analysis subtracting the base flow speed. What we have for this is called Kelvin-Helmholtz. Okay, and if you go to some mountainous areas, you are bound to see some clouds of this form. Okay, and the other thing that I want to highlight is, if even if you do the convective instability analysis, the linearized analysis will be probably holding only in this regime where the perturbations are small. Most of the things that you see, that is already in the nonlinear regime. Hold your horses there. We'll try to play this movie again when we introduce turbulence, and this is a very classical route or transition path of turbulence. So, right here from the plate you can say that a laminar flow is coming, it is getting unstable, the instabilities are growing, and far downstream those grown instabilities are causing the flow to be turbulent. And maybe we can switch on the light now.